So, hello everyone and welcome. This is the Prague Seminar for Mathematical Physics, and today we have a kind guest, Marvin Dippell from Salerno University in Italy. And Marvel brought for us a very compelling topic, and it is global homotopies and differential Hochschild cohomology or cohomologies, depending on time. Okay, so.
Thanks a lot for the introduction and the opportunity to talk today. So I want to present a joint work with Chiara Esposito, Jonas Schlitzer, and Stefan Waldmann. As we already heard, it's about global homotopies for differential Hochschild cohomologies. So I essentially want to present kind of the new proof for a classical theorem, the HK, the Hochschild-Rosenberg theorem, but which gives kind of an improved version. So yeah, first I should also say it is on the archive, and you can find the archive number here, which is okay, nobody needs the archive number if you just, I mean, it's the same title as Photoshop, so you will find it. Yeah, so if you want to look up details, you should find them there. But I hope to give you everything you need today. So rough overview of what I want to do with you. So it would be like 3 parts. First, a little motivation, why I personally am interested in this stuff and what the HKR, the Hochschild-Rosenberg theorem, actually is. So I will give a little introduction using motivation from deformation quantization. The second part is kind of the main part of my talk. So here I want to prove and show you the techniques we use to prove an improved version of the HKR theorem. And as you can see, it's kind of we use 2 tools, and I will tell you more about that later on, but it's kind of a simple calculus and a fine stuff. And then, depending on time, in the end, I want to show you some kind of first applications of these new results and how this can be used in the future. Okay, so let's start with a little bit of motivation. Since I'm here in the mathematical physics seminar, right, I start with quantization. So quantization in general is the idea to kind of go from classical physics to quantum physics, right? Now, in deformation quantization, you would start on the classical side by giving a classical mechanical phase space in terms of a, let's say, symplectic or more general Poisson manifold. So it's a smooth manifold here with a Poisson bivector field. Now this is a phase space for the classical side, but we already know that on the quantum side, we cannot expect to really have a phase space, right? Quantum mechanics is usually formulated in terms of the algebra of observables. So first step would be, let's rephrase our classical phase space in terms of observables. So we just take the algebra of smooth functions, real or complex values in our smooth manifold. We have a commutative product, just a pointwise product, and the Poisson structure on our phase space gives us the Poisson algebra structure on this commutative algebra. So we have a Lie bracket that is compatible by the Leibniz rule with the pointwise product. Now, in deformation quantization, the idea is, well, this is the classical commutative algebra of observables, and the quantum algebra of observables should be something non-commutative. So let's try to deform the classical algebra a little bit in such a way that it becomes non-commutative. So we want to go to the quantum observables, and I only want to talk about formal deformation quantization. So here I introduce formal power series on the functions. And what we want to have is now a deformation of the pointwise commutative product that makes this into a, hopefully, well, in general, non-commutative algebra, which we interpret as our algebra of observables for the quantum side. So what is this product? Now, this is, in general, the star product. So it should be a bilinear map on the formal power series of our function algebra with values in this formal power series. Well, it should be a multiplication, right? We want to have an algebra, so we want this to be associative, but not necessarily commutative. This is the quantum part. And it should be related to the classical side by a deformation. So we want that if we take 2 functions and multiply them with our star product, in lowest order of our formal parameter, which I call h bar, so it's just a formal parameter at this point. In lowest order, we just want to have the commutative pointwise product of functions. And then we get some higher order terms depending on some operators C, R. Now, we're coming from differential geometry, right? From the classical side here with the smooth manifold. So it's kind of natural to assume that these operators CR should be differential operators in both slots. So those should be bi-differential operators here. Okay, so this is kind of the meaning of we have a deformation of our pointless product, but we also want that the classical Poisson bracket corresponds to the quantum commutator on the quantum side. And again, we do not want this to be strictly true, but only up to higher orders in H bar. So if we look at the star product commutator in order 0, it vanishes because we have our pointless product here. In order 1, we want that we obtain our classical Poisson bracket, and then we get some higher order terms. Actually, you can also kind of forget about this last condition here if you additionally forget about the Poisson structure. So just deform the pointless product, and then you will always reconstruct some Poisson bracket as the lowest order term of the star product commutator. So just deforming the pointless product gives you a star product, and then you can reconstruct kind of the classical Poisson bracket you deformed. So that's the general idea of deformation quantization, but now the problem is, okay, can we always do that? Can we always deform our pointless product into a formal star product or not? And there are classical techniques. So essentially, this notion of a star product, let's say up to these differential operators here, is nothing but a deformation of some associative algebra in the sense of Gerstenhaber from the 60s, 50s, 60s, I think. And in this algebraic deformation theory, we know that we can look at the so-called Hochschild complex, and this kind of gives us a lot of information about the deformation theory of our algebra. So in this setting, let's assume we have some associative algebra A with multiplication here, think of it, functions on our smooth manifold, and we construct the so-called Hochschild complex by looking at linear homomorphisms from the k-fold tensor product of A with values in A itself. So coefficients in here just take k inputs and one output. So that's just a graded object. What is our differential? This is really the classical Hochschild differential. We have phi, which takes k inputs. We want to construct delta phi, which takes one input more. What can we do? Well, we can just apply phi to the last k inputs and multiply with the first one. We can apply phi to the first k inputs multiplied with the last one, or we can apply phi to all the inputs, but then we have to multiply two neighboring elements together. Okay, classical formula, you can check this as to 0, it is really differential. There's another structure on this Hochschild complex which we will need, which is the so-called cup product. Pretty easy. If we have two cochains here, we just take the tensor product, and then we multiply the results together in our algebra. All of that together gives us the differential graded algebra, which I denote by HC, so the Hochschild complex. And I told you this is important for deformation theory. So why is that? Let's give a look at the lowest orders in Hochschild cohomology. So if we look at order 0 in cohomology, we just get the center of our algebra. If our algebra was commutative, this is just the algebra itself. In first order, we get the quotient of the derivations of the algebra modulo inner derivations. Inner derivations are derivations given by commutators of a fixed element. In particular, if you again assume your algebra is commutative as the algebra of smooth functions, for example, the inner derivations just vanish and we just get the derivations here. Okay, so far, so good. But now in second cohomology, it becomes interesting really for deformation theory. So here we get equivalence classes of infinitesimal deformations, so not full formal deformations, but only deformations which are associative up to first order. Okay, you could say if we have something like that, you want to have a full formal deformation, can we extend it? Part of the solution lies in the third Hochschild cohomology. So the third Hochschild cohomology gives us obstructions to the extensions of these infinitesimal deformations to the next order. For example, if this vanishes, we know we can always extend and get a full formal deformation. Okay, so this is all just well-known stuff. Just a little bit of motivation here. Now, I started with the example of the algebra of functions on smooth manifold. The question would now be, can we compute Hochschild cohomology in that case? So let's assume that our algebra is just the algebra of smooth functions. And then I told you already a start product should not be any deformation, but we wanted a deformation where these operators CR are always bi-differential operators. So we're not interested in the full Hochschild complex, but in a subcomplex which consists of multi-differential operators. So it's homomorphisms from the K4 tensor product, where in each slot we have a differential operator. And now for this subcomplex, there's the classical Hochschild-Rosenberg theorem telling us that we have a morphism from the multi-vector fields considered as a complex with differential 0 to the differential Hochschild complex with our Hochschild differential. And in cohomology, this morphism is really an isomorphism. Okay, and moreover, this H gamma is not just some map, you can really write it down easily, it looks like that. So you insert a multi-vector field, and what you do is you kind of consider every single vector field as a derivation of the algebra, so it's just a v derivative in the direction of the vector field here. And then you take the cut product of these differential operators. So applying to function means just evaluate every vector field on the function, multiply things together, and then enter some trisome. Okay, this kind of classical HKR theorem, Hochschild and Rosenberg, was done in '62, but not in the setting of differential geometry, but in the setting of algebraic geometry. So it was not exactly this result, but in the years after that, well, there were many proofs of this differential HKR theorem. For example, there was one by Gibbs Wormsley, people like that. But all these proofs have some drawbacks, I would say. So for once, most, if not all of the proofs are local. So what people did is, well, choose a chart, choose coordinates, compute cohomology in coordinates, and then glue things together. Which works nicely, but if you, for example, look at a little bit more structured situation, like you have a Lie group acting on the manifold, and you want to look at invariant Hochschild cohomology. Well, then gluing stuff can create problems. I mean, there's no guarantee that you get an invariant partition of unity. So working locally is really a problem. So that's one problem with the kind of classical proofs of the HKR theorem. The other one is, well, you have a quasi-isomorphism here, but it would be nice to also have a quasi-inverse, telling us kind of an inverse here, which really becomes an inverse in cohomology. Moreover, it would be nice to have a homotopy which really tells us in which sense this quasi-inverse is a quasi-inverse, so a homotopy that kind of gives us primitives to closed cocycles. Okay, so these are kind of the two major issues I want to solve with the following proof I want to show you. So let's come to the second part. So I want to give you the strategy of an improved version for this HKR. So the general strategy, we know what we want in the end. We want to have the HKR map from multi-vector fields to the differential Hochschild cohomology. And on the right-hand side, we know this is just differential operators, multi-differential operators. In the first step, what we are going to do is identify this complex of differential operators with a complex I will call the co-algebra complex of the vector fields, which will be essentially nothing but the symbols of the multi-differential operators. Now, why should we do that? Because the interesting thing is that in this isomorphism, we will hide all of our geometry. Everything differential geometric will be completely hidden in this isomorphism. And then in the second step, I will show you that we can compute the cohomology of this complex by purely algebraic means. And we can do it in a really, really nice fashion so that we get a quasi-inverse homotopy and everything will be done globally. So the second step will be to connect this coalgebra homology complex with some sort of Chevalier-Eilenberg complex, where we have what we call the Van S double complex with it. And you see these two morphisms here, these will only be quasi-isomorphisms, but in the end we will have an isomorphism in homology. And this second part will be purely coalgebraic. There's no differential geometry in there anymore. And okay, what I did not tell you is what is the definition of this Chevalier-Eilenberg complex, but it will turn out to be essentially just the multivector fields. So it's a two-step proof. We first do the geometric part, and then we consider this Van S double complex in coalgebraic fashion. So let's start with the geometry part. So what we have to do is we choose the covariant derivative on our smooth manifold, and from this we can construct the following map. So sometimes this is called the symmetrized covariant derivative. What does it do? It takes symmetric tensor products, tensor powers of one forms, and increases the symmetric degree by 1. Okay, how does it do that? I'll just give you the formula so that you can be sure it's not complicated. Yeah, but you don't have to remember that. But essentially, we just take the derivative of phi in direction of all vector fields, and then we take the derivative inside of phi in all vector field directions. Okay, this is interesting because with this we can really write down what I would call a symbol calculus. So this is this isomorphism op, because it constructs out of the tensor algebra of the symmetric algebra of the vector fields a differential operator. And this map is given as follows. So we plug in an element of our tensor algebra. We want that it is a differential operator, so we have to evaluate it on functions. And then if you look just at this insertion part here, what it does, we apply our symmetrized covariant derivative, this d to the nabla, to the f as many times as the degree of our xk is. Right? Essentially, we take Taylor coefficients of our function f, and then we insert the symmetric vector field. Right? So what we do is essentially we differentiate the f in the direction of this x1 to xk. And in the end, we multiply stuff together. Okay? And well, you can show that this is really an isomorphism of filtered objects. And this is some classical stuff. The earliest we could find was some lecture notes of Palais from 65. So nothing complicated here in some sense. Okay, that's nice. We can now identify our differential Hochschild complex with this tensor algebra of the symmetric algebra. Problem is we want to compute cohomology, and we have on the right-hand side the differential. So what is the differential on the left-hand side? What is the differential on this TS, this tensor algebra of the symmetric algebra? Okay, for this, let's give a look at the symmetric algebra as a coalgebra. So from now on, V will always just be some module over some algebra A. We don't really care. And then we construct the symmetric algebra, and I quickly want to recall that this is a co-unitary coalgebra. You all know that. Okay, so we have the shuffle coproduct on the symmetric coalgebra, which is essentially just given by splitting our symmetric our element of the symmetric algebra into two parts, and then we symmetrize the first and the second part kind of separately. So this gives a co-commutative, co-associative coproduct on the symmetric algebra of V. And additionally, we also have the co-unit, which is just given by projecting to degree 0, symmetric degree 0, so just to the algebra, the underlying algebra. Okay, from this structure, we can construct another co-multiplication coproduct we will need, namely the reduced shuffle coproduct, which is just the shuffle coproduct, but we remove the terms where all of the x's kind of end up in the left or in the right leg. Right? Okay, with this reduced shuffle coproduct, we can now define the differential on the tensor algebra of the symmetric algebra of V. And this complex I will denote by this CCA, so this is co-algebra complex. We call it the co-algebra complex of V, even though it's the co-algebra complex of SV, but just to keep the notation kind of managed. So what does the differential look like? But essentially, we just apply the reduced shuffle coupler to all of the tensor factors. And we do it in such a way that we have the usual kind of Leibniz formula, let's say. So we just extend our reduced shuffle coproduct as a graded derivation to the tensor algebra. This becomes a differential, and magic, in the end, it is really the correct differential that corresponds under our isomorphism from the symbol calculus to the Hochschild differential on the right hand side. Okay, with that, we are now kind of done with the geometric part. We have really identified an isomorphic complex, and it only uses the co-algebraic structure on the symmetric algebra of the vector fields. So going back to our strategy, the first part is done. So the second step is computing the cohomology of this co-algebra complex here. And now we can really do it for algebra for arbitrary modules. Okay, well, there are different techniques to do that. I mean, this has been computed in the literature before, probably you know that. I want to give a specific proof, and I want to quickly recall the motivation why we do it that way. If this motivation doesn't help you, you can completely forget it, because all the following constructions you can understand without that. But the rough idea is that the symmetric algebra of the vector fields on M are kind of isomorphic to the polynomial functions on the cotangent boundary. So the functions on the space T star M, which are polynomial in 5 directions. Well, if we now look at the tensor algebra of the symmetric algebra, this can be identified with polynomial functions on T star M, where we take as many products here as we have tensor degrees. If you look at this, it might look familiar, because then you can actually see that the differential corresponds to kind of usual group or groupoid complex differential on the group or groupoid, as you want to see it, which is just equipped with a abelian multiplication plus. So really, really simple group. So in some sense, what we want to compute algebraically here is just some sort of group cohomology. Okay. Group cohomology computing is kind of simple, because we know we have a Van Est theorem telling us that group cohomology is essentially the cohomology of the corresponding Lie algebra. Okay. So the idea is now, well, mimic this Van Est construction for a group or a groupoid cohomology on the algebraic side. So we want to construct kind of a Van Est theorem telling us this co-algebra cohomology here should be the same as some sort of Schirali-Allenberg cohomology. And everything I'm showing to you afterwards is essentially already hidden in the papers by Van Est from the 50s. We just kind of reformulated in algebra and didn't use kind of the smooth function versions of the groups. Okay, so what do we do? We want to compute the cohomology of this co-algebra complex. So this was the tensor algebra of the symmetric algebra. And now I introduce a new double complex, which I call the Van Est double complex, which is given by the tensor algebra of SV. So this is just the co-algebra complex here. Then we have another additional factor of the symmetric algebra, and in the end we take the Grassmann algebra of V. And this is bi-graded, and as a grading I want to use the tensor degree as the first one and the Grassmann degree as the second. Okay, you can think of it as just this usual grid, and we have some obvious morphisms between the co-algebra complex and this Van Est double complex. Right? We can just embed the co-algebra complex into this one by simply setting this SV and the wedge V part to 1. So this is our map J, and the way back is just, okay, we project in the SV and in the wedge V part, we project to degree 0, and then we obtain something in the co-algebra complex again. So we have kind of obvious injection and projection maps here. Okay, I said this is a complex, but so far I didn't give you any differentials. So let's start with the horizontal differential. So we can construct a horizontal differential which raises the second degree, so the wedge degree, by 1. How do we do that? We apply 2 some x from the tensor algebra, phi from the symmetric, psi from the Grassmann algebra. What we do is we simply do nothing on x, and we use the shuffle co-product on the symmetric part and move one of the legs to the wedge part at the end. So here I use the usual notation for the shuffle co-product. And in order to take the wedge product here in the last part, we need to project to degree 1 in the symmetric part. So you can check easily this is really differential on each of the rows here. Now, question would be, can we compute the cohomology of these rows? And I say yes, this is really, really easy, and I actually can give you a homotopy to compute this cohomology. And what does the homotopy do? Well, it should decrease the anti-symmetric degree by 1. So this time we keep our x. We use the shuffle co-product on the anti-symmetric algebra, which is essentially the same as the shuffle co-product on SV. And now we move one leg to the middle part. So delta moves one leg from the middle to the right, k moves one leg from the right to the middle. Then we can easily check. This is a homotopy showing that J and Q are actually quasi-inverses, and the cohomology of each single row is concentrated in degree 0 and exactly given by the respective degree in our coalgebra complex. Okay, so we have computed, or at least I told you, you can compute the cohomologies of the rows, but as you see, we have not yet used our differential here. A bit strange, but stay with me for a second. Now this should be a double complex, so we can also connect this double complex in the other direction, in the vertical direction, with another complex. And this other complex I denote by CCE, so this is for Chevalier-Eilenberg, and it is just the complex given by the Grassmann algebra of V. And again, we can relate it to the double complex by I, which just inserts it into this last part here and sets the tensor and the symmetric degree to 1. And we can project down by simply project to symmetric and tensor degree 0. So we again get maps of complexes here, and this time we get a vertical differential. What is this vertical differential doing? Well, it should increase the tensor degree by 1. Here we have now two choices. We can first apply the differential of the coalgebra complex I showed you before. So this is essentially just the shuffle co-product on all of the tensor spots. So we increase the tensor degree by 1. Or what we can do is we take again the shuffle co-product on this SV part in the middle and move one of the legs into the TSV part. So we increase the tensor degree by 1 here. And again, I can give you a homotopy to compute the cohomology here. And this is again really easy. You take the tensor algebra part, and you just move the last tensor slot into this artificial new SV slot in the middle. And the old phi is just projected away using our code. And again, you can check this is really a homotopy, making I and P quasi-inverses, and showing that the horizontal cohomology of this finite double complex is really just given in degree 0 by the respective degree of the Chevalier-Eilenberg complex. So, putting this all together, we have our algebra complex, which we want to compute. We have this finite double complex, and this relates it to the Chevalier-Eilenberg complex. Problem is, the Chevalier-Eilenberg complex and the coalgebra complex are related to the bigraded module, this finite double complex, but not really to a common differential, right? They were related to different differentials. So what we would like to have is, well, we would like to relate both of the complexes on the outside to the finite double complex using the same differential, which is just the sum of the vertical and the horizontal. But well, I mean, if I change the differential here, maps will not be Cohomologies morphisms anymore. We don't have homotopies anywhere, so we get a problem like this one. Okay, what is the solution? Well, the solution is well known. Little recollection from homological algebra. So what we want to use is the classical homological perturbation lemma. Okay, what does it tell us? It tells us, given such an object, which I call a deformation retract, and this object consists of two complexes, C and D, with two maps between the complexes, and a homotopy, meaning a map on D of degree -1, fulfilling these properties. So P is a left inverse of I, but I is not necessarily left inverse of P, but the failure of the invertibility is kind of controlled by our homotopy. And as you can easily see, in cohomology, the left-hand side vanishes, and I appear really inverses. Okay, so homological perturbation lemma tells us if we have such an object, and if we have this perturbation of the differential on the right-hand side. And by perturbation, I mean that P, such that if I add this to the differential, it still squares to 0. So it is a new differential on the right-hand side. And this perturbation should be small in a certain sense. Being small here means that identity plus BH is invertible. And in our case, you can always write it like that, like the usual von Neumann formula. Don't be afraid of the infinity here. So what you can show is that if you apply this on elements, for every element, this is just the finite sum. So no analysis needed. Okay, the homological perturbation lemma says now if we start with a deformation retract like that, and we have a small perturbation, we can construct a new deformation retract, where we have on the right-hand side the new differential is given by the perturbed differential, but then all the other structures also get perturbed a little. So our delta, our differential on the left-hand side gets perturbed, the I and P get perturbed, and also the homotopy. But moreover, the homological perturbation lemma tells us specific formulas how these perturbations look like. And might look scary at a first glance, but essentially it's just, for example, if you look at H, P, and I, it's just the old map, and then you kind of compose it with the perturbation coming from B. Right? So you take just the old homotopy, perturb it, you take the old P, perturb it, you take the old I, perturb it, and for the differential you add again the like perturbed version. Okay, you don't need to remember that, I just want to say these perturbations, you can, at least in low degrees, you can write them down really by hand. They are really explicit. Okay, back to our situation from before. What did we have? We had the coalgebra cohomology, still with differential 0, and these were related by J and Q to the finite double complex, but only with this blue partial, the horizontal differential. On the other hand, we have the Chevalier-Eilenberg complex, which was related via I and P to the finite double complex, but only with respect to the vertical differential. So what we do now is we view our blue partial here, plus the delta, so we view the green thing as a perturbation of the blue thing. And we apply our homological perturbation lemma. Which means we have to deform everything, so we deform our homotopy, we deform our J, which luckily here does not get deformed at all. We have to deform our Q, and we deform our differential on the coalgebra complex, which was 0 there before. And now, actually, it becomes exactly the coalgebra differential we want. So you could say by chance, but this perturbation gives us really the correct differential here, which we needed for the Hochschild complex. Okay, so we know now that the coalgebra cohomology here is the same as the cohomology of the finite double complex. We have quasi-isomorphisms and beyond. And now we do the same thing again in the vertical direction. We view partial as a perturbation of the green delta and apply our homological perturbation lemma. We have to perturb our P, we have to perturb our I, but the I stays actually the same. We have to perturb our homotopy, and we have to perturb the zero differential, and it turns out the perturbation is again zero. Okay. So now we also know that the cohomology of this Chevalier complex here, which is really, really easy because we have zero differential, is the same as the cohomology of the Van Estado complex. And we have a homotopy for that. Okay, now composing these two directions gives what we call the Van Est deformation retract. So we really get quasi-isomorphisms between the Chevalier cohomology of V and the coalgebra cohomology of V. And we have a homotopy which is just a combination of these perturbed maps that we're talking about. Okay, you could say, well, this might be a really horrible map, which is somehow true, but it's just a combination of all these H and Ks and stuff like that I showed you before, which was just move tensor products around, right? There was nothing too complicated in there. Okay, so we are finally there. The last comment I want to make at this point is you can do actually this construction also in the case that you consider the coalgebra complex with values in some co-module. So just quickly, we could turn on kind of coefficient co-module in all of these three places. And then say, well, what we have to do now is perturb the total differential again one more time. And then we do the same stuff as before. We perturb the differential here, so we perturb the complexes and the maps, and we again get a deformation retract for the Chevalier complex and the coalgebra complex with values in some homotopy. Okay. Now let's put stuff together. So we wanted to compute the differential Hochschild cohomology for smooth functions, right? So in our first step, what we did was identifying the differential Hochschild complex with the coalgebra complex. This was our symbol calculus. Here we needed to choose a covariant derivative. But now after that, we just computed completely algebraically the cohomology of this coalgebra complex and really got these, what we call the Van Est isomorphisms. So these are quasi-isomorphisms between the coalgebra cohomology and the multi-vector fields. Okay, now you see already we just make this identification and we end up with the Hochschild-Grossmann-Rosenberg theorem now with an explicit homotopy. So again, what do we have? We have our multi-vector fields here. We have as the HKR map from the multi-vector fields to the differential operators, just the composition of this Van Est map, which itself was just a composition of these horizontal and vertical maps, and our identification of the symbols, this symbol calculus. And I mean, at this point, this is just some map, but I call it HKR because it is really the simple HKR map that I showed you by the way. But now we not only have the information of this map and that it is an isomorphism in cohomology, but we actually get a quasi-inverse by using just the inverse of the symbol map and the quasi-inverse from the Van Est double complex. And moreover, we get a homotopy. Right? And recall again, everything we did was global. We never chose coordinates. We never need to go local and then patch things together. So all our construction here are inherently global, and all these maps really have explicit formulas in the sense of that we have these sums from the homological perturbation lemma. And in the end, we get a quasi-inverse for the HKR map, and we get a homotopy which really tells us, okay, if I insert here now a closed cochain, this theta of delta vanishes, so our closed cochain is really given by HKR minus 1. So this is kind of the part in cohomology, plus something which is exact. And the exact part can really explicitly be computed using our homotopy. And in applications, this can be really, really helpful because now, if we have structured situations, as I told you before, for example, if we have group acting, we can look at the properties of this homotopy and of the quasi-inverse of the HKR map to really understand if maybe everything here is also compatible with this stuff. Okay, that was the big.
Sorry, quasi-inverse is usually used in analysis, so inverse are too compact operator. You avoid into analysis and topology. What does it mean quasi-inverse?
Okay, with quasi-inverse, it just means it's a morphism on the complex level, which on cohomology gives an.
So this is quasi-isomorphism. This is usually called quasi-isomorphism.
Yeah, okay. I'm not sure if I mixed that up, but okay. So HKR is a quasi-isomorphism, and we have a quasi-inverse, meaning a map on the complex level, which is not an inverse, but in cohomology it becomes an inverse.
Yeah, thanks.
Okay, more question about that proof. Okay, if not, then I can spend the remaining minutes, or a lot of time, so we can look at many applications. So I just want to show you a few applications to give you a taste of why this specific proof can be seen as a little bit better version of the classical HKR theorem and what to do with that. So first example would maybe be this one. So we start with an additional embedded enclosed submanifold of our manifold M. And now, well, we always chose a covariant derivative. Now we want this covariant derivative to be adapted to the submanifold. So meaning, when we restrict it to the submanifold, it is again a covariant derivative on the submanifold. Okay? What you can do then is check that the symbol calculus we defined at the beginning is really an isomorphism, but this time also between the tangential Hochschild complex. So these are differential operators which are tangent to the submanifold, meaning if you restrict them to the submanifold, they are differential operators really on the submanifold. And the tensor algebra of the symmetric algebra of the vector fields tangent to C. So we just globally define vector fields which on the submanifold restrict to vector fields on the submanifold. Okay, if we have this isomorphism, well, and we check again, this is also an isomorphism really for the differentials, for the complexes. Now, if you look at the left-hand side, you see, well, this is nothing but the co-algebra complex of a slightly different module, of a submodule. But all our computations for this Farnes double complex, or we related this with the Schiller-Ellenberg complex, blah, blah, this did not depend on the specifics of this module. So this will work here immediately. So from the construction of our proof, we immediately get some kind of tangential HKR theorem, again giving us an HKR map from the tangential multivector fields to the tangential differential Hochschild complex with a quasi-inverse and a globally defined homotopy.
A quick question. So I guess so the HKR map is not depending on the explicit choice of the connection, right? So
yeah, yes, it is not. So the HKR map is actually not. The inverse is. So the quasi-inverse and the homotopy strongly depend on your choice of covariant derivative.
Okay, because I was just wondering, so here you have to choose a connection that is adapted to C.
Yeah.
But okay, if it doesn't depend on the choice, then I mean you could also choose a different one, right? But you're saying then what would not work is the inverse and.
I mean, as long as you choose adapted ones, all of them will work, and you just get kind of isomorphic deformation complexes. You will have a different homotopy, but it will still be isomorphisms in cohomologies. Well, if your covariant derivative is not adapted to C, the problem is you don't get this symbol calculus. But at least in the case that your C is really an embedded closed submanifold, you can always find that.
Sorry, could you please repeat what does it mean adapted?
Okay, by adapted I just mean if you kind of restrict your covariant derivative to vector fields on C, and you take a vector field on C, you take the covariant derivative into the direction of another vector field on C, what you get out really is again a vector field on C. So you can just restrict it to covariant derivative.
So a little bit their tangential spaces.
Yes. Yes. Okay, so here we essentially needed to do nothing new. We just had to make sure that we have a simple calculus and then we apply our fun-S double complex gymnastics and it works again. Okay, a little bit more interesting, I teased this a little bit before. So, for example, if we say we have a lead group acting in a smooth way on our smooth manifold. And this time, let's say we have a covariant derivative which is invariant under this lead group action. What can we do? Well, you can actually show that the simple calculus will be equivariant with respect to the G action here. So you can restrict on both sides to the G invariant subspace. So we get an isomorphism between the invariant differential Hochschild complex and the invariant elements in this tensor algebra. Now we cannot directly apply the truths from before, right? Because this invariant things is not just some coalgebra complex of another module. It is invariant stuff inside the coalgebra complex. But if you recall what we actually did to compute the coalgebra complex, well, we constructed the symmetric and the tensor algebra, we took tensor products with the symmetric algebra and the Grassmann algebra, we wrote down all these homotopies and differentials, but all they did was kind of canonical. We just moved around tensor slots a little. So in the end, what you can show is that all these constructions are really functorial. So whenever you have a morphism between the two modules, you get in the end morphisms between the fun-S deformation defects, kind of intertwining the homotopies and the quasi-inverses, stuff like that. So in our case, if we start with the lead group acting, we can well, look just at the automorphisms given by the lead group action. And since everything, well, the simple calculus is equivariant and all the fun-S constructions are equivariant because they are functorial, we can also restrict our HKR maps in the end. Well, they will all be equivariant, so we can restrict them to the invariant objects. So what we get is a general invariant HKR theorem for lead group action with a homotopy, we already defined, HKR map quasi-inverses between the invariant Hochschild cohomology and the invariant multivector 15. As far as I know, this result has not been done before. So there was some results by Miaskivsky a few years ago who computed the invariant Hochschild cohomology in the case of a proper lead group action. But he really used the properness in the sense that he had to average kind of over the orbits of this thing. In general, for a general lead group, you cannot do that, but with this construction, it's kind of immediate, just by factoriality. Okay, if we can do it for a Lie group, we can also do it for the algebra. If we assume we have a Lie algebra action and we have now Lie algebra acting invariant, Lie algebra action invariant covariant derivative, we get again simple calculus on the invariant elements, and with the same arguments we get an invariant HKR theorem now for an arbitrary algebra action. Okay, one more. Another structure we could have on our manifold is that of a fiber bundle. So let's assume we have a surjective submersion between two manifolds, and assume we have an adapted covariant derivative, meaning we have a covariant derivative on P, we have a covariant derivative on M, and they are kind of compatible with the projection. And well, just in order to be able to write down stuff in a better language, assume that we have chosen also a horizontal bundle for the tangent bundle of the P. What we can do then again is, well, look at the simple calculus, and a differential Hochschild complex that has been considered in the literature before is this one. So we take the multi-differential operators on the base manifold, now with values in the differential operators on the total space. Okay, I did not introduce to you what is the Hochschild complex with values in some module, but I guess you know what that is, or you can figure it out yourself. Okay, what you can show now is that the simple calculus I wrote down in the beginning is an isomorphism between this Hochschild complex and something that looks like that. So it's a tensor algebra of the symmetric algebra of horizontal vector fields. So this is essentially the coalgebra complex we have been working with the whole time. But then we have tensor, the symmetric algebra of all vector fields on TP. So what that actually is the coalgebra complex of the horizontal vector fields with values in this co-module here, this STP co-module. And the coaction of this co-module is just, well, use the shuffle co-product and then project one of the legs to our horizontal boundary. Okay, if this is an isomorphism, I already told you that we can generalize this on S double complex stuff to the case where we have a coefficient co-module. And with this, immediately we get an HKR theorem adapted to any surjective submersion. And the cohomology will be concentrated in degree 0. It will just be given by the vertical differential operators on P. Okay. Also, this cohomology has been computed a few years ago by Kuhle and Bordemann, I think. They used that for deformation quantization of surjective submersions. They computed this again in a local way. I would say it's really, really complicated because you have to be really careful when you glue. But you can also do it kind of in this easy way. And what you additionally get is, again, a globally defined quasi-inverse and a globally defined homotopy, which they were not able to achieve. Okay, so as a last example, just to wrap this up a little, we can now combine things. We can look at principal bundles. So we have a principal bundle over M, so we have a Lie group acting on our total space P, and we choose a principal connection on P and a covariant derivative on M. That should again be compatible. Then again, what you get just by combining the two results from before, from the Lie group action example and the surjective submersion version, you get immediately an adapted HKR theorem, and what you get now is that the invariant Hochschild cohomology of M with values in the differential operators on P is given by the invariant vertical differential operators on P. And also this thing here on the right hand side, we didn't just come up with that. This is used in deformation compensation for the deformation compensation of principal bundles. So having a quasi-inverse here and a homotopy, both globally defined and pretty explicit, can be really useful.
I know it was you quantize connection really on that side, or just sections of TP, because sections of TP can be connections on these values in the Lie algebra are connections. So actually, it's moved from the point of view of physics a bit further.
Okay, let's say I'm not too familiar with what they really did when considering deformations of principal bundles, but I would say they did not deform the covariant derivative here. What they were deforming kind of is the product structure on M, so to get a star product here, and kind of deform, I think, the sections of P, I'm not sure, but as a module over the star.
It is not further proof. It can be also quantized because it can be seen as principal connections on P as well as in P equivalent resolution.
Maybe
it is like multiplication you use in the further commutative objects function level, or something technical, which is that side. But
okay, so let's say for us this is just one example where we say, okay, we can recover their results and even improve them a little bit. What you do with this is your own business, right? Okay, so let's wrap this up. What I wanted to show you is kind of a new proof of the classical HKR theorem, which uses really well-known and I would say simple tools. So what we used was the simple calculus to get the geometry under control. And then we just use really, really basic coalgebra stuff of the symmetric coalgebra and the homological perturbation level. So all these ingredients are kind of easy and well known. But still, I would claim we get an improvement in that we have really explicit formulas for this stuff. So in your examples, you can really compute the quasi-inverses in many cases. Everything is inherently global, so you do not need to go to coordinates and glue stuff. It is highly adaptable, as I hope I showed you. You can really, not just the result, but also the strategy of the proof, you can easily adapt to more structured situations. And I would say maybe even the most important thing, you get explicit global homotopies. And this really helps if you want to apply your HKR theorem at some point. It really helps if you can compute primitives of closed groups. So I hope I showed you that with really easy techniques, we can actually improve the HKR theorem and obtain some new results. Thanks a lot.
Thank you very much. I would like to open space for your questions.
So multi-vector fields and multi-differential operators, there are also differential graded Lie algebras, right? And the HKR map is not a morphism of differential graded Lie algebras, right? It's failing to be the algebra morphism, right?
Yeah, okay, yes. So we have, let's see if I can find, okay, yeah, okay, so I only talked about kind of the differential graded algebra structure, and I left out the Lie part kind of deliberately. Because we know in general already this HKR map is not compatible with the bracket structure. So you have the Gerstenhaber bracket on the right hand side, you have the Southern bracket on this side, but this will not be a Lie morphism between these brackets.
Right. My question would be like, can you use this quasi-inverse that you have here kind of to explicitly write down the failure of this being a Lie algebra morphism?
I don't know. I think it can be really hard, because if you would be able to do that, you would be really close to continuous result, right? Okay, so one way maybe to see that is, so we have on this side we have the Gerstenhaber bracket, and one way to view what you just mentioned, I think, would be to use the how do you say, the homotopy. Okay, so you could pull back kind of the Lie bracket here to this side, but what you will get is an L-infinity structure on this one. Now the question would be, is this L-infinity structure just given by the Schouten bracket? If that would be the case, we would be finished and would have kind of continuous.
So it's probably not.
So it's probably not. But yeah, you're right. If we would be able to kind of recompute the L-infinity structure on this side, which we get by pulling back, and comparing it with continuous, might help to understand it a little bit better. I mean, one problem is what you really, so whatever you pull back here will depend on the chosen covariant derivative. So it can be quite nasty, I think. Yeah. But this is something I wanted to look at in the next time, just, I don't know, look at it in the flat case where we don't care about the covariant derivative, and just see if we can compute some lower orders of the L-infinity structure here. But so far, I don't know.
Any other question?
Yeah, this perturbation written here, HKR composed with HKR -1,
yes,
is nilpotent. Why is it nilpotent? Only because of the exteriorness of this lambda on the left-hand side, or it was assumption? I was confused. I didn't.
Sorry, what do you mean by nilpotent?
You said at one point that some perturbation was nilpotent. The was
yes.
nilpotent.
This one here, right?
Wait, one, right?
Is that what you mean?
Yeah.
Okay, this essentially just isn't kind of locally nilpotent by the fact that B reduces the degree by one, H reduces the degree by 1. So if you apply this,
yeah, so this finiteness of Grassmann algebra.
Yes.
Finite boundedness of the complex.
Right. Yeah.
I would maybe have a question. How is it possible that HKR map is not connection dependent? Once you created this via some specific choice, or you mentioned?
Okay, so no, it does not depend on a specific choice. I think the reason is kind of what does the HKR map do? Well, it maps the multi-vector fields to multi-differential operators. So it's really slow. But it only kind of works with. No, I'm not. Here we are. So it only works with differential operators of degree 1, right? We only get kind of derivations here.
Okay.
So it is kind of reasonable that the covariant derivative does not play a role, because the covariant derivative you essentially need to get the higher differentiation always under control. So let's say I don't have a more algebraic reason why this really happens. It's just, yeah, if you compute it,
okay,
it's not depending on.
Because it's on functions also.
Because it's on what do you mean?
No, you have only sections. No, I cannot say this. You have only sections of trivial vector bundle, but you don't have sections of tangent bundles. So the question of connection is geometric. It's true.
Yes.
Any other question? Maybe from online audience or? Is there any perspective to generalize it for a case of higher principal bundles, for instance? Once you consider this.
Okay, yeah, no,
And
yes. Never thought about that.
Because you can maybe pass in this direction by assuming some G action via viewing this as some action groupoid.
Yes.
And I'm not really sure how to work, but incorporate this, not considering the truncated case, but also the higher degrees of their action groupoid. But
okay, yeah, I've never thought about it this way. Could work. I think at the moment you have kind of a well-adapted symbol calculus, the rest is kind of easy. So come to this question, kind of, can you find a good covariant derivative in this case, which gives you a symbol calculus? Yeah, would be interesting.
so doesn't seem to be the case.
Actually, the spectral sequences were used for the different isomorphisms you just used, didn't mention there. For this, you mentioned this isomorphism of Chevalier, of algebra, and also of the final complex. So they are usually proved by considering some spectral sequences. So. But in double complex, usually you can really double complex, you can compute spectral sequences of double complex, and if you have some nice vanishing on edges,
right,
you can relate it to this.
But as far as I know, if you work with spectral sequences, you usually don't get like homotopies for the cohomology, right? You would know that in cohomology it would be you could compute cohomology. But yeah, then maybe there's a way to do this also as a sequence. I don't know. But there are cases, I guess.
You can also use homotopies as well, of course.
Yes, in some instances, the spectral complex, it's the same as homological perturbation.
Okay.
In some special cases.
Yeah,
you can do either this or homological perturbation.
I would say if it's in some special cases the same, then this should be one because it is a really, really simple case.
Yeah.
So then maybe you can view this as a spectral sequence.
No, I know that the spectral sequences are used in the canonical isomorphism that are on your picture, these three isomorphisms. and then you don't need this spectral things at all. So,
Yeah.
so just curious whether you.
No, I don't know.
Okay, so there is no other question. Thank the speaker again.
Yes, it's nothing like this. Complicated. It's just the only question I still don't know when the deadline is for something.